Hello, it's good to see everybody here today. Thanks for joining me to talk a little bit about compiler plugins. Uh, I'd been wondering what a crowd would look like that wanted to learn about compiler plugins, and you all look a lot better looking than I imagined. That joke hit a lot better at home in my mirror. If you guys aren't laughing at my jokes, I'm assuming that you just can't hear me in the Listen Wi-Fi app. Just thinking about that. So that's what I'm going to go with and make myself feel better. As you can probably tell, I'm wearing this really awesome DroidCon 2015 shirt, which was my very first DroidCon 10 years ago. And I thought it'd be cool to take a look back at some of the things that were popular back then, DroidCon 2015. So DroidCon 2015, I was using a awesome Moto X by Google. Google owned Motorola for about like 6 months or so. It was a very short time, but it was a really awesome phone. And even gave us a spot for the dimple, and then eventually that turned into a fingerprint, and it was awesome. We were targeting Android 21 Lollipop at the time. Most folks probably don't even have that as their Mint SDK anymore. But 21 was like, it really turned the corner for things. It was really awesome. And oh, by the way, we were still 1 year away from Kotlin. We were in this really different warehouse than this one, much smaller facility. Oh, and this guy that was there, he knew absolutely nothing about Kotlin. So fast forward today, I am a DE at Capital One, and I know slightly more about Kotlin. How much more, it really depends on who you ask I work with. And as I've became a tech leader, and in any respect to that term, I've learned that I have to become very opinionated, and sometimes opinionated on things that I didn't think I needed to be opinionated on. And I'm sure that probably resonates with many folks out there. Luckily for everyone that works with me, I'm very opinionated, and I'm never shy of sharing those with folks. And the challenge becomes, how do we share and scale those opinions with our large organizations that we have? And I, again, love sharing my opinion, but there's only one of me to go around. And so, of course, this becomes really, really important when we're working on large-scale initiatives, such as maybe, rollout of enterprise-wide Compose. And we really need to find ways to scale those opinions and streamline the work for our teams and our developers. So let's take a look at some of the tools that I have found useful to do this. First and foremost, the foundation of everything that we should be doing is static code analysis. This includes like lint and detect. And here we can do things, especially within Compose, like restricting mutable parameters, enforcing parameter ordering, ensuring our view models are not being used as state, etc. And there's some really, really great open source rule lists out there for both lint and detect. And I'd encourage you to check those out. And what's really great about static code analysis is it's really just an analysis of the AST. It reads your code. It's very non-intrusive. It doesn't change anything, and it runs independently of the compilation process itself. And then, of course, when we're talking about streamlining our developers, we really need to push past the boilerplate and making sure that our developers are not having to write all that code. And KSP is a great tool into generating new code. Again, this is additive. It adds new code, but it doesn't modify any of your existing code. And it runs as a part of the compilation process. And last, and certainly not least, since this is what we're here to talk about, is compiler plugins. And what we can do with compiler plugins, especially after K2, is really quite broad and quite frankly, maybe a little too powerful. Compiler plugins are the transformative option. We can inspect, we can validate, we can add, we can modify code, and its execution is the compilation process itself, right? It's hooked into exposed extensions that the K2 compiler makes available to us. And of course, each one is a little bit more approachable than the next. While we can do everything that in a compiler plugin that, say, static code analysis and KSP can do, it doesn't mean that we really should just default to compiler plugins. We need to use the right tool for the right job. And it's, of course, the maintenance that the compiler plugins come with is quite large. And so we don't want to just always default to those. And so what is the right tool for the right job? So when we look at like lint and detect, can our analysis or diagnostic or maybe even sometimes additive code be done with AST inspection? So in that case, lint and detect. Are you adding new code or that's not modifying existing code? KSP. If you need a diagnostic that needs maybe some semantic information that's not available as a part of the AST, or maybe you're modifying or adding or deleting new declarations, that's going to be a compiler plugin. And of course, if you decide you do need a plugin, you really should start by understanding a bit about the compiler itself. I'm certainly not an authority or an expert in the compiler, and we've just experienced a big change as we moved from K1 to K2. But there's some really great resources out there that I'd encourage you to check out. Kotlin Conf 23 was a great year for compiler plugins, and there's actually a few other talks happening here as well on the topic. So certainly check those out. But of course, if we're going to talk about compiler plugins today, we're going to need to know at least a little bit of the basics. I'm going to attempt to talk about the K2 compiler, and I'm going to focus only on the K2 compiler in just one slide. So that means I'm going to wildly oversimplify it, but hopefully we understand enough so that we can talk about the R plugins effectively. So the K2 compiler is broken down into a front end and a back end. The front end is generally responsible for checking grammar, structure, semantics of your code. And the front end is really what your IDE uses to show those little squiggly lines and the errors when you're getting when you're writing your code. And at the end of the front end process, we're generating the IR as input to the back end. And so the first step as a part of the front end is the parser, which checks grammar, and it starts to generate the syntax tree. And then from there, the syntax tree is then used to begin constructing the front-end intermediate representation. This is a new concept within K2 and often referred to as FIR. And this performs some desugaring. It adds some semantic information back into the AST. This is the really powerful part of the FIR tree. Next, we're going to pass it through some checkers. And this is going to output some errors and warnings and some suggestions there for you. And as we'll soon see, this is one of our first opportunities to actually plug into the compilation process to provide our own checkers so that we can provide our own errors or warnings. And finally, we begin moving on. And after we've gotten past our checkers and everything's going well, we start the generation from our FIR to our backend intermediate representation, which becomes the input to our backend. The backend's primary job is to take that generated target, to take that backend intermediate representation and then generate the target or machine code. So think about this as like, getting the Java bytecode at the end of this, the native LLVM or JS or whatever it might be that we are targeting. So the first step in the backend is the IR generator. This receives that common non-target specific intermediate representation that the front end generated. And this is where we're also going to have a chance to provide a plugin. And we can hook into here so that we can modify that IR for our needs. There's an optimization. This is a general optimization. Will remove dead code. It will refactor things like maybe moving from an if statement to a when block, and so that it can be a little bit more performant, et cetera. And again, this is very general. No matter what code you're targeting, or what target you're targeting, you're going to go through the same optimizer here. Next, we're going to have the machine-dependent optimizer. So this is often referred to as lowering, and this optimization is different based on the target that you have set. And finally, at the end of this process, we start the generation of our Java bytecode, native LLVM, JS, whatever, again, our target is. And that is the K2 compiler in one slide. So if we, again, now we've decided we need a plugin. We know a little bit about the compiler, but we now need to choose whether we're going to build a front-end plugin or a back-end plugin. So, really generally, the best way to kind of tell this is if we're looking for a new diagnostic, an error, warnings, or in some cases you need to add new code, that's going to be a front-end plugin. If you need to change a method body, a statement, or a call site, you need to delete code, you need to inject something new, that's going to be a backend plugin. And there's some great examples that I've got listed up here. What's really helpful about these is that these are provided by Kotlin or by JetBrains, and they're great to check out and reverse engineer. You can find some really great patterns and samples in there, especially as you're moving from the K1 to K2 compiler. This is a great way to get started. So today, and I hope that we can see some of this code all right, we're going to walk through the creation of two plugins, a front-end plugin and a back-end plugin. Our front end plugin, what we're going to try to do is we're going to restrict what types of composals can be called within specific slots. So if you have been working in Compose, you know it's pretty popular to uh, open up slots when you're building out your components. You use these every day. So when you like write a button component, for example, where you're able to add the text, that's a slot that that the button component has left available for you. But sometimes we want to make sure that we are providing some level of customization without giving the developers the entire world of options, right? Like we want to say you have access to use these three composable functions. You can pass whatever modifiers you want in those, but you cannot go and just use a generally available composable. And so what we're going to do is we're going to create a front end plugin that will check out a receiver type for this at restricted scope on our slots. If that exists, we're going to make sure that we only allow composables that are members of that receiver's class. We're going to also look at a backend plugin. This plugin is going to be very simple. We're going to add log statements to our composable block so that we can track compositions and then recompositions over time. We also want to take it a little bit step further, and we want to be able to write UI tests on this. So I want to be able to write a UI test that says we should only see 3 recompositions based on this user input. So if you write a test, user clicks a button, I want to make sure that I only experience a certain number of compositions, and it doesn't change over time. This is really, really helpful, especially with new teams who are still getting used to the concept of state hoisting. Implementing unit testing or UI testing that has the ability to track your compositions is really powerful. But first, before we can get started with building out those really awesome plugins, there's a little bit of setup that we need to do. So this is the project setup that we're going to look at today, and I promise you it doesn't look as bad as it is here. It doesn't look, it's not as bad as what it looks here. So let's look into each one of these a little bit more. I would assume that everybody knows really what our app module is, so we're going to skip past that and jump into our Gradle plugin. So we'll use a Gradle plugin to configure our compiler plugin. This is really, it's not a requirement, but if your compiler plugin has different features that you want to enable and disable, the Gradle plugin provides a handy DSL for you to take those configurations and apply them to the compiler plugin itself. And we'll see some of this in some of our sample code that we go through. Last thing that this also does here is that we have a chance to apply any necessary runtime dependencies. So let's say that we have a backend plugin and we're going to add new code. Maybe that new code belongs to a different dependency. We want to use our Gradle plugin here to apply those necessary dependencies as well. Abstract all that away from the developer. We also need a CLI plugin. This is what receives those configurations from the Gradle plugin and ensures that they are provided to our compiler plugin itself. So again, we start with the Gradle plugin. Developer sets up and says they want this feature on, this feature off. That Gradle plugin is going to pass those configurations into your compiler plugin through the CLI plugin. And you can see that the CLI plugin is actually in my sample code base here. It's going to be a part of the same compiler module. And then next is our actual front end plugin. Again, this is the plugin where we're going to show compilation errors based on that restricted scope annotation. And there are a host of different extensions that we can tap into here, and specifically checker extensions. We're going to use the additional checkers extension here, but there's the declaration generation and then the support type ones as well. There's a host of different options for us. And we're going to set those up within the plugin registrar that we're going to look at in a little bit. Next, we have our backend plugin. Again, this is where we're going to add those tracking of our testing and our composables and our composition tracking as well. For our project, we're going to actually have this in the same module as our front-end plugin. You may choose to break them up depending on how granular of options that you want to give your developers to apply these tools. With backend plugins, we really have one place that we can plug into, and that's the IR generation extension class. And finally, our runtime dependency. So in our sample here, this is where we're going to define our restricted scope annotation. Additionally, this is where we're also going to write the functions that we're going to inject into our composables via our backend, right? We don't want to have to write those tracking functions via our intermediate representation. While we could, it would really not be fun. So it's much easier to go ahead and have those functions already written out as public functions that we can then just add new declarations into the various composable blocks that we're going to be looking at. So let's take a look at a little bit of the code. We first have our Gradle plugin, and I won't go into too much detail here because there's plenty of resources out there on Gradle plugins here. The few things I want to highlight here is that we're going to extend the Kotlin compiler plugin support plugin. I don't know, by the way, I don't know what's the count on the number of times I've said plugin. It's probably a lot. I've seen a few people taking drinks out there for some reason. This just provides a handy entry point to applying our compiler plugin itself. And so here it provides us an entry point to applying our configurations to our plugin. That is, again, is going to be sent to our CLI. And then, as we mentioned before, we can set up any runtime dependencies. In my case here, you can see that I'm adding the runtime dependency that is a part of my project, where, again, that we're going to have our tracking functions and our annotation declared. Next is our command line plugin, and again, this is going to be within our compiler plugin module itself when we look at our project setup. And we can configure this to what our CLI expects here. So this function here says that we have two different configurations that we expect. They're not required, but this is what we're going to look for as part of our setup. And then we need to also process those arguments as they come into through the command line itself. Next is our plugin registrar. So this is where we tell the compiler that we have some plugins that need to be processed as a part of the compilation process. And we first and foremost, we're going to make sure that the compiler knows that we are supporting K2. Hopefully you all just default this to true, and nobody has to worry about the K1 compiler. In this example, I'm going to just apply my front-end plugin. You can see that I'm not wrapping it in any configuration checks. I'm just going to blindly apply this plugin. And you can see that I've got this register extension and then this FIR register. And we'll talk a little bit more about that when we talk about the front-end plugin itself. Down here is where we're going to apply our back-end plugin via the IR extension. We're going to pass in a message collector, and then you can see that we're also passing in a CLI plugin configuration itself through the logging enabled. The message collector, by the way, so if you're not familiar with this, it's a really handy way to add messages to the compilation process. So this could be either for your debugging purposes, if you need a way to, step through your code, or maybe you want to provide some sort of message out to the developer that you've added a configuration or what have you. The message collector is a way to do that. Through the samples that I have in this code, you can see the messages that we're applying through adding the info tag at the end of your Gradle task here. And that's it. That's the foundation to what we need for both of our plugins. Once you have that set up, you're now ready to run and really build as many front-end plugins and back-end plugins as you want. And so we're going to start again with the front-end plugin. So as a reminder, what we're trying to prevent is developers from using unrestricted, globally available composables within the scope that is intended for like a self-contained or only support specific composables. And we're going to do this by checking a Lambda and seeing if that Lambda has a receiver. And if that receiver is there, if it's restricted via the restricted scope annotation. If that is all happen to be true, we're going to check to make sure that the composable functions that are there are members of that receiver. You can see hopefully you can see in the code down there that we have variant 1 and variant 2. We're going to allow those because those are member functions. We could even call non-composable functions, no problem. But if we try to call a composable that is not a member of that receiver type, we're going to throw an error. So let's look at our example application here, and this is kind of how I would set it up. So first and foremost, we have our receiver object here of custom scope, and I've got this at restricted scope annotation on it. You can here imagine that this is a composable component. Imagine it's a little bit more robust. What we're going to do here is provide a slot, and that slot is going to be an extension of custom scope so that we have now custom scope as a receiver in that slot. And then finally, what this allows us to do is, again, down here you can see that the text composable is not allowed, but we can call things like logs or member composables of that restricted receiver. All right, so we've looked at the app code along with the basic Gradle and CLI plugin setup. So now we're ready to jump into that front end plugin code. So first, we need to tap into the FIR register. So when we were looking at the plugin register earlier, what we were doing is we were registering the front end registrar, and this is where we can apply various different types of extensions. In my case here, I'm adding a checker extension, but we can again tap into other types of extensions as well. The K-Tools checker extension that I have here in my sample extends the additional checkers extension, and there are a host of different checkers that you can tap into. We are going to look at the function call checkers, which means that we are going to visit every function call that is declared. And check to see if that function call is abiding by the rules that we've set. In this case here, most of the work that we have set up here is going to be in this K-Tools restricted scope checker. Before we get into that code, we need a way to show the user, the developer, an error within our front-end plugin. So in order to do this, we will register these errors via a message renderer. And this is just really allowing the compiler to have like a formatter so that when we provide the error, the error and then the error body, that it can format it. And so you can see down here in that image that it will take and format some of the outputs so that it shows up nicely for the developer to find, so they can find the code and then they can find what went wrong. All right, so we're now within our FIR function call checker, which is where, again, the main body of work is going to happen. And it looks like there's a lot here, but once we break it down, that's really not that much. It's all the magic happens here. So first and foremost, again, we have this check function, and this check function is going to be hit for every new function declaration that we are finding in our compilation process. So, for example, I've got a little code snippet on the left. Let's imagine that we are inspecting that text composable function as we go through this code. So first thing that we're going to do is check to see if this function call declaration is being checked from within a lambda. If our function call is not from within a lambda, we can ignore this function, right? So if we're just calling a composable in any other way that it's not within a lambda, we don't need to really continue on. We are only worried about lambdas with restricted receivers. Next, now that we know that our function call is happening within a lambda, we need to check to see, do we have a receiver type? And then, is that receiver type annotated with our restricted scope? Because if we're within a lambda or a slot that doesn't have a receiver, or that receiver is not annotated, we really don't care about it. So we call a function down here, get restricted receiver type, that inspects the lambda to get the receiver type. And then it's going to check if that type's class is annotated with the restricted scope. Notice down here, I've got this little box, if you can see it on the cone Kotlin type. So if you remember back to when we were talking about the compiler itself, we talked about one of the first steps we had was the AST, the AST being our abstract syntax tree, but our FIR is not just an AST. It's an AST with semantic information, or you might call it like a semantic graph. And so the cone Kotlin types that you'll see is really what is kind of that semantic glue for our FIR tree. Otherwise, we would just have an old AST. All right, so we know that we're calling a function. We're within a lambda, and that lambda has a receiver with a type that is restricted. So now we're going to start digging into this function a little bit more, so that we can check it out a little bit more closely to see if we need to inspect it. Here, what we're going to do is we're going to get the FIR named function symbol, which just simply is the FIR representation of that function call. And what we need to do is check to see if this is a composable. Again, if we're looking at any other function that is non-composable, we really don't care about this. We can let it pass. Of course, in your plugins, maybe you'd want to extend this to do something else. But in our world here, we're only looking at composable functions. And then here is a little bypass we have to put in place. So in our custom slot component that we were looking at earlier, that slot itself, when we go to invoke it, it would actually throw an error with this work. So we need to provide a little check to see, like, are we in a slot itself, so that we can bypass some of these rules and allow it to pass through. So that's all that this is doing, is it's just making sure that the invocation of our slot itself doesn't get blocked by the rest of our work. All right, so if we made it this far, and hopefully we're still tracking, we have determined that we're in a lambda. That lambda has a receiver type. That receiver type is annotated with our restricted scope annotation. We also have determined that we are a composable, and so which means that if we're to allow this function to proceed, that composable needs to be a member of our receiver, a receiver class. And so we call this function is call allowed. And within this function, you can see we do a few things. One of those being that we get the owning class ID of that receiver type. We go and get the Kotlin code type of that, so that we can check to see, is this function is the composable? Does it belong to that member, or excuse me, that receiver type, or does it belong to maybe a subtype of that receiver type? And if it does, we're going to let it pass. And if it doesn't, we're going to show a nice little error saying that's an invalid composable invocation. And that is it. We are now able to add our annotation and get errors on any composable that is not a member of our restricted receivers. Pretty straightforward, right? And again, this is not, I'll tell you that this is not a holistic example. If you're sitting back here, you're probably thinking about like, well, what about remembers and a few of those things? You would certainly need to expand upon this to allow some of those other use cases to pass through, so that you aren't blocking some other composables that should be allowed in these samples. All right, so let's take a look at our second plugin. This again is our backend plugin, and it's actually a pretty simple one, even though we're going to add some cool new capabilities. So as a reminder, what our goal is here is that we want to track compositions and recompositions by throwing some logs whenever those things happen. And we also want to make it to where we can run assertions or run tests based on those compositions. So I want to make sure, if you can see in my sample here, that I run an assertion on that I should only see this build UI composable column button, because I've got 2 buttons. Then when I perform an action, I should only see 2 new compositions happen. I shouldn't see anything else. And that's what we're going to look at here today. So this is the sample code, very simple UI that we're gonna follow within our demo. We have a column and 2 text fields and 2 buttons. And those buttons are going to increment and decrement a number. Very, very simple sample that most of us have probably built in some regard or another. What we're going to do is, in that increment and decrement, they're actually going to call updates on our view model that's going to then update our state object and then re-output those through the process here. And then what's really going to happen here is that we want to make sure that we can add essentially logs to these various block bodies. And now in my sample here, and what we're going to look at is we're going to look at only composable block bodies. We're not going to look at the composables themselves. That's just a choice that we made for this work here. But you may choose that you want to actually track composable function calls themselves. So the difference here is that, again, I'm going to be visiting block bodies, but what we're not going to see is that I'm not going to output compositions and recomposition logs based on text, the text composables, because those don't have block bodies to track. And then we also want to be able to write a test so that we can ensure that we don't accidentally recompose in various cases. Again, this is going to be really helpful for developers that are still getting the hang of that state hoisting, that as they make changes to the UI, that they're not introducing extra recompositions when they don't need to. So here we have a UI test, and this UI test, we have access to a composition tracker and this object, and then from within that object, we can run some assertions on the compositions themselves that are taking place. But where does this composition tracker come from? Well, it's going to come from our plugin runtime. Again, as I was mentioning earlier, when we are injecting code into our backend, when we're adding new declarations to these block bodies, we don't want to have to write all of this code in the IR itself. We just want to be able to ideally reference something that's already written, and then just say, hey, add a new function declaration right here, function call declaration right here. And so what we're going to do is we're going to define this within our plugin runtime. And so this is actually a very simple, on our plugin runtime, you can see that we have this, we're using a static composition local of in order to provide our composition tracker. This is going to be helpful so that we aren't actually, when it's non-test, that we're not adding any tracking, and we're not tracking recompositions when we're in a non-UI test scenario, right? If the composition tracker is not present, we can't add any composition tracking. You can see next we have this composition tracker slot or builder function here. And from within here is just a nice handy way that we're going to provide our composition tracker to the composition tracker local. And then this track composition function down here, this is really where all the heavy lifting is done. This is what we're going to call or add the new call declarations from within our backend plugin. This adds our composables to the local composition tracker, and it also logs our recompositions to the logcat. So putting this all together, track composition is actually what's going to get injected in each one of these composable block bodies. And so again, remember, since we're modifying existing code in function declarations, this must be a backend plugin. So let's look and see what that looks like. So as I was mentioning earlier, we really only have one entry point into the backend, and that's via the IR generation process. And so here we're going to be an IR extension. And what's really interesting is that this generate function, every time it gets hit, it's going to be provided the entire module worth of code. So if you're in a multi-module application, it's going to get hit multiple times, but once for each of the modules that is being processed. And it's given the entire IR for that module, and then you're gonna step through it appropriately. And now for us, what we also want to do is make sure that we're not injecting our tracking to test code. So you can imagine the infinite loop that we might get in there. So we're going to bail out if we're starting to process a test module here. And then finally, this is where we let the module fragment know that we're going to transform some code, and all that transformation is going to happen in the KTools tracker down here. And this KTools tracker is an IR transformer class that provides a host of different visitor functions that we can dive into further. And then down here, this tracker context is a state object. This is optional. There's actually an IR transformer void where if you didn't want to do this, you don't have to. I actually find this is very useful. This is a state object that can be used to pass relevant state information from one visitor function within our IR transformer stepping. You can update that state object with various information so that you can kind of get an idea of, okay, I'm in this file or I'm in this function, and get an understanding of your surroundings when you're only looking at like one function block. So let's take a look at what that looks like. So as I mentioned, the real work happens in this IR transformer. It looks really big, but I'll point out here that these three functions really aren't doing anything. You'll notice that what we're actually seeing here is that we're modifying the state, the tracker context, and we're just updating and saying, okay, we're in this file, we're visiting this function, and some of the nearest function calls that are around us are these ones. And we're just adding that to our state so that we can provide it better information as a part of our logs that we're going to add on our recompositions. So you can imagine if you have a composable that is, there's the same composable that is in multiple files. This will provide a better log if we can tell the developer that this file, this composable, is recomposing versus just a random composable. Again, we're wanting to call track composition with our composable block body. So to do that, we first need to visit the block body within our IR. So you can see this visitor function that we're looking at here. This is where all the magic happens. And the first thing that we need to do is check out if this block body is actually a composable block body. If this is any other type of block body, if it's not a composable, we can really bail out. We really don't care to proceed any further. So I'm doing a real simple check. What I'm doing here is I'm just going to look at the other function calls that are happening within this block body. And I'm saying, okay, are any of those function calls composables? If they are, then I can assume that my block body is assume that our block body is a composable itself. And then right here, I'm going to add a little message to the compiler, letting the compiler know that I'm going to track this composition. Again, if this sends a little message to the output during the compilation process, so that we would have something for debugging or just extra information to the developer about what we're doing. This build tracker function, we're going to dive into the body of this here in a little bit, because this is where we're going to add the new declaration itself. But you can see here that we're taking the response from build tracker, and we are adding it to the existing body.statements. And so if you see down here, it's body.statements.add, and I'm adding it at position 0, which means that the new function declarations that I am adding will be the very first function call within that block body. All right, so within our build tracker function, this is again where we're going to define that new track composition function that we're going to use. So when we are tracking our compositions, sometimes it's a little helpful to pass in a little timestamp to get a little bit of some ordering of what's happening. And this first part is actually adding a function call to a declared utility function that's getting the current time. So you can see I'm just calling this get current time. I'm setting it up in the IR call implementation and setting it as a variable so that I can use that function declaration later. And then finally, we're ready to define our track composition function itself. Here we can see that we are adding the first argument. The first argument in our case is the log or the name of the composable that is recomposing. We're also adding an argument that's indicating whether we want to actually log this to the logcat. So this came from the Gradle plugin itself. So if you imagine that it came from the Gradle plugin, that configuration, and it's all the way going to be passed down to here, letting the track composition function know whether we want to log this to the logcat or not. And then finally, we can pass the current time function as a higher order function and as the last argument here. And then so you can see down here, this fun track composition is exactly what we are getting added down here. And then so now we can test and see our logs. And here we can see that our test is providing the composable tracker. And then we have our various assertions. Again, we start with our first assertion. This is going to be all the things that, all the block bodies that should be composing originally. We reset that, we run some user interactions. And then what we want to do is assert that the composition is only a build UI and column, and that we don't see any that we don't see any compositions for button. And of course, we can see our compositions and recompositions being printed as log statements, which was the goal of our backend plugin. This code is available for you to see and check out and extend on as well here at the KTools plugin. And I hope you enjoyed this talk. If you have any questions about compiler, the compiler plugin, compiler plugins, or different use cases, feel free to find me afterwards. I'll be happy to chat about them. Otherwise, thank you for joining me today.